Hello everyone, and welcome to your video on the GCM theorem. Now, let me just start by saying that this is an excellent example of a horribly named theorem, because when we look at GCM all in capital letters like that, we know it's supposed to mean something, but we don't know what it means. Well, it gets even worse, because what it stands for is don't write this down, the generalization of the converse of the mid-segment theorem. Get it? GCM? That's what it stands for. Yeah, okay, that's ugly, right? Well, wait, it gets worse. There's also this thing called the CGCM theorem, and that is short for, don't write this down either, the converse of the generalization of the converse of the mid-segment theorem. What? Yeah, I know. I completely understand your hatred of all of this because I share it. I really do. So we are going to put these theorems in our notes, and I'm going to, distill down for you what it is that they're talking about. But since we're talking about the mid-segment theorem, I think that we should just review what that says for just a minute. You already have this in your notes somewhere, and it said this. It said that if you have a nice, beautiful little triangle, and you take the mid-segment of this line, that means that those two sides, or those two segments, are congruent to each other, and you draw a line to the mid-segment of the other side, so that this is congruent to that. It says that we automatically know two things. We know that these lines are parallel to each other. And we also know that this mid-segment is half the length of the big side. So x and 2x, right? That's what the mid-segment theorem said. If you take the mid-segment of this side and draw it to the mid-segment of this side, you automatically get parallel lines, and they are in a 1-to-2 ratio to each other. So that's what the mid-segment theorem says. So all we're doing with this GCM theorem and the CGCM theorem is we're taking this idea and we're just expanding it a little bit more. And I'm not even going to make you, do the proofs to know that this is correct. I just want to have you put it in your notes, and then we're going to learn how to work with it. So let's put in our notes the GCM theorem, and that can be found on page 309. And this is what it says. It says a line parallel to one side of a triangle intercepts proportional segments on the other two sides. So let's draw an example. So let's draw ourselves a nice little triangle here. That's a lovely triangle. And we are going to draw ourselves a parallel line across. But it does not have to be in the middle, right? Because it does not have to be a mid-segment. So I'm going to draw my line up here. Okay? And I know that this is parallel to that, right? This little line here is parallel to that larger line right there. And if this segment is called X, and this segment is called Y, and this segment is called P, and this segment is called Q, then I know that X divided by Y is going to equal P divided by Q. right? X divided by Y is going to equal P divided by Q. In other words, there's some sort of predictable relationship between these segment lengths when they are made by drawing a parallel line. And just to be clear, you could have X divided by P is going to equal Y divided by Q. That's also the same. You're just going to have a good looking proportion somewhere. So let's do an example of this particular concept. So let's say that we have this and this, and these two lines, oh, there you go, and those two lines are parallel to each other. Okay? And let's say that we know that this is 2 and this is 4, just pretend. And this is 8, what is this side over here going to be? If you said 16, you are right, because we're going 2 times 2 makes 4, 8 times 2 makes 16. So there has to be some sort of relationship between those two numbers. Now, I did not do a very good job here because this does not look like 2 and that does not look like 4. So let me draw one more so that it looks a little bit better. Let's draw, we'll do a right triangle like this. And we will draw a line like this. And if I know that this is 3 and this is 4, this is 3 and this is 4, and I know that this is 8, can you tell me what X is? Well, I certainly hope so. Let's see. I will get an orange marker here and we will make a formula. I'll say top part over bottom part equals top part over bottom part. So that's going to be 32 equals 3x. Divide both sides by 3. X is going to equal some weird number. Let me see. 32 divided by 3 is, yeah, 10 and 2/3. But so I'll just leave it as 32 over 3. And that will be the side length there. All right, now let's look at the CGCM theorem, which also needs to go into your notes. CGCM, which is on page 310. This is a theorem. And it says that if a line intercepts proportional segments on two sides of a triangle, then it is parallel to the third side. So if we have a triangle and we have some sort of line, and we say, I wonder if this line is parallel to this line. Well, you would figure out if A divided by C equals B divided by D, then the two lines are parallel. The two horizontal lines. Then the two horizontal lines have to be parallel. This has to be parallel to that. So that is the CGCM theorem. Before I let you go, let's just do one example. So let's say that we have this triangle right here. And we have A, B, C, and then this is DE. And our question is DE parallel to AC? Well, let's figure this out. Let's say that this is 4, and let's say this is 10, and let's say that this is 5, and let's say that this is 14. Is DE parallel to AC? Well, if it is, then this ratio has to be true. So we'll do 4 over 10. Does that equal 5 over 14? Well, let's see. 4 divided by 10, isn't that going to be 0.4? I'm pretty sure, yeah, 0.4. Does that equal 5 divided by 14? No, because that's 0.36, let's say. Not the same, not parallel. So that's how we could use our CGCM theorem. If the two ratios were equal, then we would know that that line was parallel.